So this is solving for the amount of energy and the amount of force needed to assemble a box. They're supposed to be equal distance apart, but I'm just kind of freehand drawing it. And it is a box of charges, and there's a 6 coulomb charge here, a 6 coulomb charge here, and a 6 coulomb charge here. And each one of these charges are separated by a distance of 2 meters. Okay. And this one's going to be A, this one's going to be B, this one's going to be C. Okay, so charge A, bringing charge A, if I were to calculate the amount of energy or work, if you will, that's needed to bring that charge in, we usually start off by saying we're bringing these charges in from infinity. That way we can ignore a lot of conditions. So yes, well, imagine we're bringing it into infinity. So the amount of work that would be needed to do that would equal the force times the displacement, or we had come up with an equation that said K Q Q over R. So that represents the amount of work, the amount of force, and I should just say work and force is going to be equal to K Q Q over R squared. And there is kind of a sign dependency there. But here's the thing. Without these other two charges, the single charge does not have the second charge to deal with it. So bringing this one single charge in requires zero work because it's not overcoming anything, and it requires zero force because once again it's not overcoming anything. There's not something pushing back on it so that I would have to do work on it, or something pulling that would mean that I'd have to do negative work on it. So because of that, there is no work in the initial conditions of this problem. When I bring this first charge in A, it doesn't require me to do anything to do it. Now, the second charge is not quite the same. So once this second charge in, this charge B comes in, this one right here, it has to deal with charge A. Okay? But fortunately enough, the equation here really doesn't change. It stays the same. So work is going to be equal to K, Q, Q over R. And force is going to equal to K, Q, Q over R squared. So I'm going to kind of solve this not by using, I'll leave K alone. I'll solve my solutions in terms of K, and you can just supplement in the value for K on this one. So Q and Q, that would be QA and QB, and QA and QB. And this R would be the distance, specifically the distance from A to B. I gotta double check that. Okay. No. It would be the distance from B to A. Sorry about that. And I know that because this term is going to be a positive term for the charges, which means that the force that is being exerted will be in the opposite direction. So if I wanted to figure out the force that was exerted on a B, it would be A to B. If I wanted to find the force exerted on A from B, it would be B from A. Okay? Sorry about that. A little bit of a mind blank. So that is going to be K, and then 6 times 6. So that's going to be this one times this one, divided by this one. And all my terms are positive, so it simply becomes a value of K 36 divided by 2, and that'd be 36 coulombs squared divided by meter. Okay. So that's the amount of work that's required to do it, and then also multiplied by K. And mind you, K is a huge number. Dealing with it over here with forces, I'm left with is equal to K 6 times 6, 4 meters, or 4, it'd be, 2 squared, which is going to give me a value of K 36 over 4 coulomb squared meter squared. Okay, so that is the amount of work that's required and the amount of force that's required to bring this object here, the 6 coulomb charge, this point B, within 2 meters of point A. Okay, So far, so good. Doesn't seem complicated at all. Now, if I wanted to bring in my third charge, so not only is everything that I've already calculated part of bringing in this third charge, because, orders of operation, I brought in A, then I brought in B, then I brought in C. So if I were to calculate the total energy of the system and the total energy or the total amount of forces that exist in the system, I have to keep track of all of that because it's all there. But I'm going to do this separately. I'm going to do this by just approaching just the charge C. And sorry, I wanted to erase that because there was so much stuff there. Just bringing in the charge C into that configuration. So I'm not... The energy is there for A to B. The work or the force is there from A to B. But all I want to do is deal with the last bit here. And let's see if I can get you to focus again. Camera. I don't know. For today, my camera is just not being fun. Come on. There we go. All right. So once again, we have a charge here. That's A. 6 coulombs. Charge here. That's B. Oh, not 6 meters. 6 coulombs. 6 coulombs. And then our charge C. 6 coulombs. And they're all separated by a distance of 2 meters. So now with the introduction of this last one, this 6 coulombs here, okay, we're going to calculate the amount of work that's required or the amount of energy that's stored. Well, first of all, I have K, Q, Q over R is my equation for work. But now I have 2 charges, so I have 2 equations for work. Now, this is the interaction from this charge to this charge, this one right here. And this is going to be the interaction from here to here. So they're not the same, they're different. And the big difference between them is the distance. Now, if the charges were different, they'd absolutely have more differences. But because I was lazy and only picked 6 coulombs here, those aren't going to change. So I'm going to have K, Q, Q, which would be K, be K 6 times 6, that's Q and Q, times R. Now R is not 2. R is 2 squared plus 2 squared square root. So 2 squared is going to be 4. 4 plus 4 is 8. The square root of that is 2 root 2. Okay, so that is the amount of energy that's associated with this connection. Now this energy we've done a dozen times before. That's going to be K 36, or 6 times 6, if you will, times 2. And I've got a glare there. Cool? So that's the amount of energy required to bring this charge into that configuration. Now, mind you, if I wanted to talk about the total energy, I'd have to include this one, which would be K 6 over 2. But because I'm only talking about bringing 6 into this group, or this C into this group, I'm not going to concern myself with the energy that's there yet. Okay. Now, forces is going to be the same way. I've got 2 charges. I'm bringing in a third charge into those 2 charges. So there's going to be 2 equations for force. And it's not going to be as easy as energy or work, because energy and work are scalars, which they don't have a directional dependency. And force does. So the force, let me eliminate this part right here, so I have the space to do it. So the force is K, Q, Q, R squared. And I'm going to put a little thing here called a unit vector. That just tells me what direction it is in. Okay? Plus K, Q, Q, R squared, R hat. And that was going to be K, okay, and that's going to be 6 times 6, so that doesn't change, times R squared. And here's where things get a little bit different. Because of the vector nature of it, I know that this single charge here is going to push this way. Okay? So I need to calculate this much force and this much force. Okay? So in order to keep everything separated, I'm going to say X and y, and that's the force in x and the force in y. Okay, so the force in x is going to be kqq over r squared, but now I'm only looking for the x component of it, which is in this direction. Okay, and I'm only worrying about this one right now. Well, that distance is still going to be 2 root 2. Now that whole thing is going to be squared because it's r squared. And I saw previously that r was 2 root 2. Okay, but that's the magnitude of it, and I need to now calculate the direction. I need to calculate that. So to get that vector to split up, like so, I'm going to consider this to be my angle, and I'm going to be looking for this side of my angle. It's cosine. And because I'm lazy and I made the triangle all the same side, I know that this is going to be 45 and this is going to be 45. Because if I bisect an angle on a square like this, I know that the whole thing is 90, and then this section and this section are equal parts, so they'd both be 45. So that would be the cosine of 45. Sort of. That was 45, but if I'm going to use a coordinate system, I really should be counting about that much distance. I should actually be counting about from there. I don't want to. I'm going to be smarter than that and just simply say that that's a negative because that's pointing in a negative x direction. Okay? And now I'm going to bring in the other side because that one is also on the x direction. That's going to be equal to k, q, q over r squared. Well, that's a plus, not an equal. Which is going to give me 6 times 6 over 2 squared. And also, this is going to be pushing in the negative x direction, so I'm going to say negative. Okay, so this is the force. Oops, I did that wrong. This is the force that one feels on this one. I need the force that this one exerts on that one, which is in that direction and that direction. McNeil, why did you do that? Well, I did that because of Newton's third law, equal and opposite forces. You calculated this one by mistake, but now I was actually trying to figure out this one. Well, it doesn't really tell me a lot of differences, except for this sign becomes positive, because now it's pushing it in a positive x direction. And oops, I said that was negative. But it isn't pushing at all in this direction. So this term goes away. So, oops. Okay. So that's in my x direction. Now in my y direction, now I get to account for this force now because it is in the y direction. And I also have an interaction here. So let's start with that interaction there. It's still the same equation, k, q, q over r squared. Okay. And now instead of looking at the cosine of it, I'm looking at the sine of it, which, because I picked 45, really doesn't make a difference. And because I'm looking in the y direction, I'm looking at this charge will push down on it. Negative. Okay. Lastly, I'm including this one, which is a negative k, q, q over r squared. And it's pointing down, so I've got my negative sign. So this is the amount of force that last charge feels in this direction, in the y direction, and this is the amount of force that it feels in the x direction. All right, thank you.